Okay, Math 352, welcome back. We're up to lecture 10, and this lecture is examples of linear programs. So in lecture 9 we basically started looking at optimization problems, and we zoomed in on linear programs, which are basically linear versions of a general optimization problem. So we looked a little bit at the theory. We looked at some various forms these things can take, but what we really didn't get a feel for is what types of real problems you can solve with these. Okay, we know sort of what's involved, what they look like, but we don't know what you can do. So today's lecture is going to be a sequence of kind of 5 mini examples that illustrate some different ways in which linear programs can get used. Okay, it's by far and away not an exhaustive list of examples. They're one of the most kind of common types of real problems that are solved at any given moment. Okay, so we're going to start off with a production example. So we have a factory. Here it goes. Here's our factory. It didn't fall down in the earthquake, still standing. And we make furniture. And we've got a cool door. Okay, so in our factory, basically we can make tables and chairs. Now, tables and chairs take different amounts of wood, and they take different amounts of time to make. And likewise, the amount of profit we make off selling a table or selling a chair is different. So, a problem that we might want to solve in our factory is, given that we make a certain amount of profit from tables and a certain amount of profit from chairs, and we're guaranteed to sell whatever we make, what should we make in a given week? Okay, so we've got some constraints, and I'll give them to you in a little table. So basically we've got constraints on wood, labour and profit, and we're looking at tables, chairs, and we've also got kind of a supply, some limitations on supply. So we can only get a certain amount of wood in a given week, and we only have a certain amount of labour available to us. Okay, so to make a table, takes 3 units of wood, 3 planks or 3 whatevers. It takes 3 units of labour, so that might be 3 days, maybe, if it's a very slow table. And we can sell it for a profit of $4 or $4,000 or $400 or whatever. To make a chair, takes a lot less wood than a table, but it's about as involved, so it takes about the same amount of time, same amount of labour, but we sell it for less profit. And why don't we just make all tables? Because we have a certain amount of wood coming in per week. We buy in 12 units of wood every week. To buy any more would involve importing from somewhere exotic and would cost us far too much. So we're basically only buying 12 units of wood in per week. Okay, labour, our workforce can only do 24 hours, or 24 units, so maybe that's 24 man days of labour per week. And, yeah, profit doesn't need an entry there. Okay, so, additionally, we have overtime. Well, actually, let's just define some variables. Overtime is available too. At a surcharge, at a cost of 2 per unit. Okay, so it costs us 2 units of money for every unit of labour overtime. Okay, so let x1 equal number of tables we build in a week, let x2 equal number of chairs, and let x3 equal number of units of overtime. Okay, now I've made a few really big assumptions here. We're a really small but kind of desirable factory, so every table and every chair we make is going to get sold. So there's no issues here of us saturating the market by making too many chairs or too many tables. We're assuming that whatever we make, we'll have no trouble selling it at all because it's so good. Okay, so or it's so cheap and nasty. You can think of it that way too, I guess. So how can we phrase this problem here as a linear program? Well, we want to maximize our profit. That's kind of fundamentally, we want to find out which combination of tables and chairs is going to yield us the most profit in a given week. So we're going to maximize over our variables x the profit. So the profit is 4 per table plus 2 per chair, and every unit of overtime we use is going to take away 2 money units from our profit. Okay, and what are our constraints? Well, we can't use more wood than we've got. So every table takes 3 units of wood, every chair takes 1 unit of wood, and we're only getting in 12 units per week, so that's all we can do. So that's our wood constraint. And our labour. Every table takes 3 units of labour, every chair takes 3 units of labour as well, and that's less than or equal to 24. But we've got overtime available, remember, so whatever overtime is, that gets added on to our 24. And obviously the amount of overtime, the number of tables and the number of chairs can't be negative, so we've got a non-negativity constraint on all of our variables. Okay, and that is a linear program. So to solve this problem is to solve this linear program. Now, a few things here that I should just comment quickly. Our linear program might give us answers that aren't whole numbers. Okay, so we're making an assumption here. Maybe x1 is not the number of tables. Maybe it's the thousand. Maybe it's 1,000 tables. Maybe we're a huge factory. Okay, maybe x2 is how many thousands of chairs. So in some sense, if we got x1 equals a half, that could represent 500. So it's close to being a continuous problem. So let me just stress that a linear program is a continuous problem. In some sense, this problem might not make so much sense. So I want to solve graphic. So like I said, it's a linear program. It's got 3 variables, so we can't use our graphical method, but we can if we assume the overtime 0. So if you just get rid of the overtime from the equation, solve graphically for the case of no overtime. That is x3 equals 0. And I'll let you do that in your own time. If you do that though, you should find answer, your optimum should be 2 tables and 6 chairs. Okay, so I'll leave that as an exercise for you to try out for yourselves. Okay, so that's a production problem. What else can we do with linear programs? Let's have a look at another one. Now we're a big oil company and we're blending fuel. So basically we've got 4 different big bins or big buckets of fuel. There they go. Okay, so this is fuel 1. And what we're trying to do is we've sort of got, each of these fuels has different properties. So each fuel has sulfur levels theta 1 through to theta 4 for each of the 4 fuels. Units per unit volume. Okay, so they have different sulfur levels. They have different aromatic levels. Okay, A1 through to A4, again aromatic units per unit volume. And we've got a few other restrictions as well. We want to make, so a cost, that's right, cost per unit volume of C1 through to C4, and available quantities need to be volume units of Q1 through to Q4. So what we do is we've got these different fuels. They cost different amounts and they have different levels of sulfur and aromatics. What we want to do, we want to make a blend by basically pouring them into another bucket and stirring it up. Okay, and we want to have with sulfur level theta, that's a capital theta by the way, is less than or equal to theta, and aromatic level less than or equal to A, total quantity equals Q with minimum cost. Okay, so what we're trying to do is we're sort of trying to minimize the sulfur and the aromatic levels, so trying to get them below a certain limit. We want to produce a total quantity of Q, and we want to do that as cheaply as possible. So I guess the more expensive fuels will have lower levels, the cheaper ones will have higher levels, and you want to kind of mix them in such a way that you just achieve those limits and pay the least money you can get away with. Okay, so we'll add in x1 through to x4 of each. Okay, so x1 is the amount of fuel 1, x2 is the amount of fuel 2, etc. So can we write this as a linear program? Well, first we want to minimize our cost. So we're looking at a minimization problem. So minimize over x C1x1 plus C2x2 all the way up to C4x4. That's my total cost. And my constraints? Well, I've got my sulfur constraint. So look at the amount of sulfur altogether is theta1x1 through to theta4x4, and that's got to be less than or equal to the sulfur level is theta per unit volume times the total volume. Okay, so that's my sulfur constraint. Right, my aromatic one looks just the same. It's not thetas anymore. A1x1 plus etc. plus A4x4. That's got to be less than or equal to A Q. Okay, capital theta and A are specified per unit volume, so we've got to multiply it by the total volume Q. Aromatic. Now we need to just think very carefully. What else do we need to throw in there? Well, obviously we can't make negative amounts. If we just solve it as is, we'll get some negative x's probably. So we need to stick in a non-negativity constraint. It's one of the easier ones to forget. Our total quantity has to be Q. So x1 plus x, etc. up to x4 is our total quantity. Now I'll often write this in shorthand as bold 1 transpose x, and that's got to be equal to Q. So note that 1 equals this vector here, 1, 1, 1, 1. Okay, so if a bold 1 or an underlined 1, if I'm handwriting, is just the vector of 1s. So that's my total quantity constraint. And finally, I can't exceed the amount I have available, so each component of x has to be less than or equal to each corresponding component of Q. There we go. So once again, I have a linear program. Okay, so we're going to change tack once more. So we've had two kind of business-like models so far. We've got production and we've got kind of fuel blending. Now we're going to look at a more mathematical problem. Well, at least what you probably think of as a more mathematical problem. So now we're back into a slightly more familiar setting. we've got some data points, and we want to fit them by some kind of model. So this is kind of like what we did with least squares. Okay, so remember, so here's my x-axis, whatever, y-axis, something like that. I want to fit a model to my data points. With least squares, what I was doing is I was taking each of these deviations and squaring it. Okay, so the residual is basically the vector of those things put together. With least squares, I'm taking the sum of the squares of each of those, and I'm trying to minimize that. So that in least squares, our problem looks like minimize over x, ax minus b, 2 norm squared, although we don't actually need the squared, so we usually just leave it off. Okay, well let's say we don't actually care about minimizing, we won't want the least squares solution, which we already know how to do. This time we want to make sure that the worst deviation is minimized. Okay, so you want to make sure that the worst discrepancy, or the worst one of these red lines here, is as small as it can be. Okay, so what this is called is Chebyshev approximation. Want to minimize worst discrepancy, and in mathematical languages that looks like this. Minimize over x, the infinity norm of the residual. Okay, so it's almost an identical problem to least squares, at least it looks like it, except that what it's doing is quite different. Instead of kind of weighting each of these things and minimizing each of them by a certain amount, now we're minimizing only the worst one. So we're trying to find the model that makes the worst case the best. Okay, so we want to find that, and we can write this in another way. Minimize over x, or we can write the infinity norm out in full. So remember, the infinity norm is the maximum, the component of the magnitude of the largest component. So it's the minimum over x, the max over the entries of ax minus b of ai transpose x minus bi, where ai transpose is the ith row of A. Okay, so this this maximum component here just finds us the biggest component of the residual, and we're trying to minimize that. So it looks kind of weird having a minimum and a maximum stuck together like that, but believe me, it makes sense, so you might just want to think about that for a second if it doesn't yet. Okay, so our objective doesn't look anything like a linear programming objective. Remember, we're trying to make an objective that looks like this, kind of a C transpose X type objective. We don't have that at all here. This looks like a big kind of mess in terms of LP anyway. So we're going to resort to some trickery to turn our nonlinear objective into a linear one. And how are we going to do that? Well, we need to change this, obviously. So first, we're going to use the following trick. First, note that minimizing over x, some objective, is equivalent to minimize over x and t. I'm introducing a new variable t, subject to if naught of x is less than or equal to t. Okay, so this is another point in the video where you may want to just pause and think about that for a second. So I'm saying that minimizing the objective function is the same basically as minimizing the upper bound on an objective function. That's another way of thinking of it. Okay, so now in this new problem, non-linear objective, now we have linear objective, but we've made some messy constraints. Okay, so if we do this, our problem becomes well, what does it become? Minimize over x and t, our objective t, subject to the maximum, just plugging in f0 from before, of absolute value of ai transpose x minus bi is less than or equal to t. Okay, so we're saying that the largest component of our residual, okay, the absolute value of that has to be less than or equal to t. But if you think about it for a second, if the largest one, the absolute value of the largest component is less than or equal to t, then the absolute value of all the components must be less than or equal to t as well. Okay, so all components of the residual satisfy ai transpose x minus bi is less than or equal to t because the largest one does. Okay, so we can write this out in full. Expanding out the absolute value just means you've got a negative and a positive part. This means that negative t has to be less than or equal to ai transpose x minus bi, which in turn has to be less than or equal to t. Okay, and our t is automatically going to be positive, otherwise it will violate this constraint. Okay, so putting the pieces together, we do get a linear program. We want to minimize. Don't forget we've added in one new variable, so we've made our decision variables vector one longer by adding t into it. Minimize t, subject to two sets of inequalities, ai transpose x. Now I'm just going to rearrange these ones up here to put the t's on the left hand side. So minus t is less than or equal to bi from the first one, or from the right hand inequality, and negative ai transpose x minus t is less than or equal to negative bi. That's from the left hand inequality. Okay, and we could put in t is greater than or equal to 0 if we wanted to, but we don't actually need to, because there's no way you can choose a t that's negative that will satisfy these two inequalities, so it doesn't actually matter, you can leave that off. Okay, so there's our linear program for infinity norm best fits. So how strange is that? Least squares, we had a nice closed form way of computing the solution, that's if we have a 2 norm, but as soon as we change the norm to the infinity norm, we suddenly have a linear program, which seems on the face of it like quite a different type of problem. Okay, so let's continue down a little tour through various applications. We've got a couple left that I want to look at anyway. This one is very similar to the one we just did. So we just did infinity norm. Now we want to do one norm best fit. So again, we're fitting a model to our data, or at least that's the picture you can think of. There it goes again. We're fitting a model to that, whatever, and this time we want to minimize the sum of the absolute values of the residuals. Okay, if you think about it, least squares is minimizing the sum of the squares of each of these components. Now if you put one of these crosses higher up, then the square of its deviation from the model is going to be pretty big, and it's going to be kind of weighted higher is going to be kind of more important than the other points. So one norm kind of gets around this by saying we're only interested in how long that is, not the square of how long it is. Okay, so now we want to do minimize over x the one norm of ax minus b. Okay, so we can write that out in some slightly expanded notation once more as minimize over x the sum of the absolute value of each component. Now, one thing I haven't really done here, which I probably should have done, our matrix A is an m by n, just like it always is. So we're dealing with the same sort of sizes of matrices as we've been looking at for our least squares problems. Okay, so we actually resort to a very similar kind of trick again. This time, for every entry of the residual, we define a variable ti such that, well, we just look at the deviation, how big it is, and let ti be an upper bound. Okay, and once again we can expand this out into two inequalities just by doing this. And ti will turn out to be positive, just like it was before. Okay, so if we want to minimize the one norm then what we're doing is we're minimizing the sum of the ti's. How does that work? Well, ti is an upper bound on how big the ith deviation is. So ti is an upper bound on the ith deviation. If we sum up all of those upper bounds, then we have an upper bound on the total deviation. I'll say that again. Ti is an upper bound on the ith deviation. Just make a little note of this. Ti is an upper bound on the ith deviation. Okay, so the ai transpose x minus bi. Therefore, sum of all the ti's is an upper bound on the total deviation. Okay, on the sum of all these things. So what we want to find, or another way of stating the problem, is we want to find the lowest possible upper bound on the total deviation. Okay, so our solution is found by minimizing the sum of the ti's. And like I said before, the ti's are automatically going to be positive, because if they weren't, there's no way they could satisfy these inequalities. So we don't need to explicitly write down a non-negativity constraint, because it works anyway. So we want to minimize over x and t, now t is a vector, same size as x, of the sum of the t's. Once again, I'll write that as a vector 1 transpose t, where t is an rm. Okay, subject to the following constraints: ai transpose x minus ti less than or equal to bi. Once again, I'm just rearranging these two inequalities and I'm putting the ti's on the same side as the x's to put all the variables together. And the other half gives us negative ai transpose x minus ti is less than or equal to negative bi. And for each of these we've got I is equal to 1 through to m. Okay, and once again, that's a linear program. So one norm and infinity norm best fits are linear programs. One norm best fits you'll find probably used a lot more often, because they have this really neat property that because they're only measuring the lengths of the deviations and not squaring them, outliers don't have such a nasty effect. They don't skew your fits anywhere near as much. So just make a quick note about when these things are used. One norm fits are often used as they are insensitive beasties. I mean insensitive to outliers and the occasional bad point. I should say the occasional because you can't have too many of them. Occasional bad data point. Okay, now the infinity norm fits. Chebyshev, or infinity norm, well, we use these when, for whatever reason, we want to minimize the worst case behavior. We want to minimize the greatest deviation. So it's kind of a different type of problem that we'll be using infinity norm fit for. We want to minimize the worst case deviation. Okay, so they are important, somewhat less common perhaps, but they're still very important. And least squares, 2 norm, is somewhere in between. Okay, now least squares, however, is a very important case because if the deviations, so let's just flick back up to our picture for a second. If these deviations, if it's known that they come from a normal distribution, okay, for the statisticians out there, if you know that these deviations are basically samples from a normal distribution, then the least squares, or the 2 norm best fit, is actually the best, at least it's the maximum likelihood estimate of the model. Okay, if you're not a statistician and you've never come across what I'm talking about before, then don't worry. But if you know that your errors are normally distributed, then least squares is definitely the one that you should be using. Okay. Alright, so there's our second of the fitting type examples. Going to finish off with one more, and we're kind of back to our more real world type stuff. So the last one I want to do is what I call a transport problem. Okay, let's say that we can be in the sea, number of islands, so 3 islands. You can think of this basically as whatever you like, and on each of these islands I have a factory, factory 1, factory 2, and factory 3. And also in our sort of network of islands, we've got some warehouses or some shops where we're going to sell or store what we're making in our factories. Just say I've got 2 warehouses on these 2 islands here. Okay, so factories and warehouses. Okay, so we should have some C, of course. Not too much, because I'm going to draw some more stuff on this picture in a minute. Okay, so these factories are producing stuff, and then they're shipping it off to the warehouses to be stored or sold. Now you can imagine that it costs more to ship, let's look at this warehouse number 2. We can imagine that it costs more to ship our stuff from factory 1 to warehouse 2 than it does to ship our materials from factory 3 to warehouse 2. But factory 3 can't make enough to supply warehouse 2, for example, so warehouse 2 does have to get some more supply from somewhere else. So you can see there's a sort of complicated balance going on here. So to ship from factory 1 to warehouse 2 has a cost of C12 per unit. Okay, and that's going to be probably quite high. To ship to warehouse 1 will be slightly cheaper, I guess. C11. To ship from factory 2 to warehouse 1 will probably be quite cheap. C21. Then to warehouse 2 we'll have a C22. And then factory 3 to warehouse 1 we'll have C31. And factory 3 to warehouse 2 we'll have cost C32. Okay, so what's the problem? Well, the problem is factory I has supply, or the maximum supply, of SI units. Okay, that's the most it can produce and ship. Warehouse J has demand of DJ units. Cij is the cost per unit to ship from factory I to warehouse J. Okay, so you can imagine that's sort of a function of distance. If you've got a little boat here, it's going to take them longer. It's going to use more coal or fuel or whatever to go along this shipping route than it will to go along a shorter one. And finally, let Xij is the amount shipped from factory I to warehouse J. Okay, so what is the actual problem? Before we still haven't defined the problem yet. Problem: meet all demands at minimum cost. Okay, so let's see if we can turn this into a linear program. Okay, so I want to minimize the total cost. The total cost is Cij times Xij. Okay, because remember it's a cost per unit, so we've got to multiply by the number of units shipped, and we're going to take the sum over all the i's and j's. Okay, so my variables that I'm trying to set are the amounts x, the amount that factory 3 is going to ship to warehouse 2, etc., etc. That's the thing I've got some control over. Subject to some constraints, basically supply and demand. So we need to make sure that for each factory, the sum, okay, that sum there, what's that? That's the amount that gets shipped in to factory J. We're summing up all the into warehouse J, sorry. We're summing up all the incoming stuff from factories I equals 1 and 2 and 3. Summing those up gives the total amount that's coming in to warehouse J, and that's got to be greater than or equal to the demand DJ for all J. Because that one just says we're going to meet all demands. Okay. For our version of the problem, it doesn't matter if you more than meet it, so long as you meet it. Okay, likewise, factory I, if we add up all the stuff that it's sending out, that's the sum over the j's, that's got to be less than or equal to the maximum that it can supply. So this constraint says that supply is not exceeded. Okay, and finally, there's nothing enforcing non-negativity at the moment, so we need to make that explicit. All of the x's have to be greater than or equal to 0 for all I and j. Okay, and once again, there we go. We have a linear program. Okay, if you've got some spare time on your hands over the holidays, then maybe you could set up your own version. Set up some islands and pirate ships and stuff, and see if you can run a linear program and see what type of, or see if you can set up a linear program, see what type of answers you can get. Okay, now we're not going to get into actually solving these things until next week, but we're getting quite well. We're getting much more familiar with what types of what linear programs look like. So one more thing to note about this problem: if the sum of all the supplies is equal to the sum of all the demands, the total supply and demand is equal, and the problem is called balanced. Okay, so if supply and demand are equal, then we call it a balanced problem. Okay, so that kind of rounds out our set of examples of linear programs. There'll be more of these to do in the tutorial that's coming up, but until then, have a good, like I said, weekend or 5 minutes or night or day or whatever it is, and I'll look forward to seeing you guys again soon. Okay, see you later.